Welcome, everybody. Today we are very excited to have Zifeng Wang present their work Prompting-based Continual Learning. Zifeng is a machine learning PhD student at Northeastern University and a student research with Google Cloud AI Research. We're very excited to hear your talk today. These two prompting papers that you'll be discussing, one is from CVPR 2022 and the other will be presented at ECCV 2022. They seem to lay some new foundation for these future prompting-based class incremental continual learning works. They avoid fine-tuning the model and they avoid rehearsal. So without further ado, I'm going to let you tell us how you did it. So please take it away.
Yeah, sure. Welcome everybody. It's a great pleasure to have this opportunity to share our works here about prompting-based continual learning. So yeah, let's get started. Okay. So yeah, maybe just get some recap about continual learning. Okay, continual learning is actually an amazing ability about human beings to adapt to different tasks sequentially without forgetting what they have learned. And they can also seamlessly leverage knowledge learned from past tasks to tackle new tasks. And this amazing ability is actually a desirable ability for our machine learning models as well, since the world is not static. For example, we want to train a robot to do object recognition, for example. We first put the robot into a zoo to learn animal recognition, and then we may want to put the robot to a different place, like garden, to learn flower recognition. And then the robot may maybe move to a farm to learn fruit recognition and so on and so forth. So we may send to the robot to different environments and to learn all different kinds of stuffs. And of course, we don't just like the robot to do well only on the final environment, like the farm. We would like it to still perform well under all previous seen tasks. So that's why we need continual learning. We want something like a single model, like the robot, to do well with a series of tasks. So let's have a bit more formal taste about continual learning. So from my point of view, continual learning is trying to adapt a single model to learn a sequence of tasks. For example, you can think about each task as a conventional supervised classification problem. And finally, we would like the model to perform well on all tasks. So we would like to evaluate the final model using all tasks. So you can kind of have like a comparison between the traditional IID setting, which is like a popular learning paradigm, between the continual learning setting. So in IID setting, we actually don't have the idea of different tasks because all data is just available at once. We just merge all things together as a single training data set, and we train our model using usual stochastic gradient descent. And in continual learning, things are a little bit different because we have like a concept of a timeline. So the tasks will be available one by one, and then each time step, your model will just be like you will just be like available for the current data from the current tasks. So you can just train your model on that. So you can see that at each time step, the model will be trained only towards a single task. After it's trained on task one, you will get some important weights for specifically for task one. And then when it comes to task two, you'll also learn some important weights for task two. But also you can see that some of the already learned weights for task one has been a little bit shifted towards task two, and so on and so forth. So in this way, when we're trying to fit all the knowledge from different tasks one by one, we naturally face one main challenge in continual learning called catastrophic forgetting. So apparently, when we try to fit one single task, we can do very well on that single task. You can see from the timeline that when we train on the very last task, like task 3, we'll get very good performance on that. But the previously performing good like model on task 1 and 2, the performance on all tasks deteriorates drastically after learning new tasks. So, which means that our model is not able to retain what is already learned there. So this usual phenomenon that like our machine learning model suffers is called catastrophic forgetting, and we're trying to address that problem in continual learning process. Okay. So here's some like mainstream solutions. I think like 90% of the papers are based on these three mainstream solutions, and I believe there are more and more people like developing new algorithms that are outside of the three or using combination of them. But I believe they're the most fundamental ones. So the first one is called the regularization-based method. As its name suggests, we just put some regularizers to constrain some important parameters for the previously learned tasks, so that during the update process, gradient update process, we're kind of protect what is already learned there. However, I think the regularization-based methods are kind of old, and always their performance is not satisfactory nowadays. And another mainstream actually is one of the best performing methods called rehearsal-based method, which is also very straightforward. So we just like buffer some past data from old tasks. And of course, the buffer cannot be super big so that we can simply buffer all the past data. Then it's not continual learning. It's just like retrain and retrain again. So we have like a limited budget. However, there's still limitations with the rehearsal-based method because the performance just deteriorates with smaller buffer size because we cannot like retain as much as we want. And also, if there's like data privacy issue, meaning that you cannot just save the previous data because of like privacy issues, you can simply not use the rehearsal-based method. And also another interesting branch of the mainstream solutions is the so-called architecture-based method. So in this kind of methods, you always have like a main backbone, and you have like different task-specific components for different tasks, so that you can just encode your knowledge in different components without like inter-task interference. But this kind of methods often, I mean, some of the newer method doesn't have to. Like they often require task identity at test time, meaning that you need to know the testing example is from which task to decide which task-specific component to use. And they often, by adding more and more task-specific components, it will introduce large amount of additional parameters in addition to the original backbone. So this kind of methods is kind of has some scalability issues, I think. Okay. And if you really think about these three kind of different learning algorithms, it actually shares the same intuition that is to preserve learned knowledge. They just do it in different ways, but the core idea is to try to retain what is already learned there by different like formats. So the natural question is that how can we come up with a more efficient and more effective knowledge preservation system for continual learning? And yeah, here comes our newer works that brings like another learning paradigm to continual learning. So let's start with the very first work, which is called Learning to Prompt for Continual Learning, or just L2P. And in this work, we actually address like multiple challenges in continual learning. So here you can see that although our method can work pretty well with the rehearsal buffer, but it doesn't require a rehearsal buffer like as a hard constraint. And also there's no need to know the test time task identity. And L2P is compatible to a lot of like various continual learning settings, including the most difficult task agnostic one. And it's actually very memory efficient. You don't have to add like loads of additional parameters to make it work well. So yeah, and you know actually our work is the first work ever to introduce the novel idea of prompting to continue learning. So yeah, hopefully you enjoy the work. Okay, so let's get some like high level understanding of L2P first. So it's actually what is exciting about L2P is that it brings like a novel continual learning paradigm into the field. So here's like a brief summary that about the high level idea of L2P. So L2P uses the so-called learnable prompts, which you can think of it as learnable parameters for now, to instruct the pre-trained model backbone to learn different tasks. So in order to understand the work better, you can think of the rehearsal-based method as a baseline comparator first. So for the rehearsal-based method, we actually do fine-tuning through all the tasks. So for each task, we have a data buffer of past tasks, and also we have like data from the current task, say task n. And through mini batching, we just kind of mix up the two sources of data together and to train or fine-tune our model. You can see here, I use the red line to represent, red dash line to represent the trainable parameters. So we're training our model backbone along the way. So, you know, our backbone has a lot of parameters. So when we update all of them, the interference will happen. And on the right is our L2P learning paradigm. So different from the left, we're kind of have like a frozen backbone that is pre-trained already on something else, and we can assume that it is we already got like a lot of knowledge there. So what we have to do is not to update the model anymore, but we have like a set of learnable parameters called prompt pool, so that whenever a task comes, you know, just first query the prompt pool first to choose some of the learnable prompts and to use that prompts to kind of instruct the model to do the prediction. So we are actually not update the model, but we're trying to update the parameters in the prompt pool dynamically so that it can condition the model better. So that is the high level idea. Okay. So before we actually see the details of the method, I'd like to bring some of the background of the idea of prompting. So prompting, as its name suggests, is like a popular idea several years ago in NLP, and it's been more and more popular these days. So the original idea of prompting is about adding some fixed instructions or fixed hint to your input. So if you look at the figure A, it's doing the mass language model pre-training, meaning it is like a very popular pre-training paradigm in natural language processing. So it just use like a sentence here and add some random mask to the sentence, and your task is to train the model so that it can predict the missing words here. So it is kind of like unsupervised like training representation learning algorithm to train like good representations for your model. And B is kind of like a fine-tuning stage. So after you do the mass language model pre-training, you can choose to fine-tune your model backbone. So here I use like a sentiment classification problem. So you can think of it as the binary classification problem. You have two labels here, positive and negative. You can encode it as 0 and 1. And here you just use like one special token, the CLS token in natural language processing to do the classification. So you can see that the mass language model pre-training and the fine-tuning are kind of two different tasks, because at least during mass language model pre-training, we're trying to predict the words from a huge set of vocabularies. But in the fine-tuning stage, at least for the sentiment classification problem, we only have 2 labels. So at least the label space is different. So the downstream task is different from the pre-training task. However, in C, this is actually like where prompting come into play. So you can just look at the first part of the sentence and just ignore the demonstrations. So if you look at the first part of the sentence, it actually has 2 components. The first one is still the input, the no reason to watch. It is the same as what we got in the in figure B, but we add one more sentence in the end here called it was and add a mask. So we kind of transform the sentiment classification problem into a sentiment word predicting problem. So by adding the prompt, we're trying to let the model to predict what is the next word after it was. So it is kind of trying to guide the model to do the same task as what we have in the mass language model pre-training. Because if we want to predict the next word, we're still trying to choose from all the possible glossaries we have here, instead of just predicting two like positive and negative labels here. So we'll come up with some word like great, terrible, good, bad, this kind of words that describes the sentiment. And then we, again, map this kind of word to positive and negative. So actually, the idea of prompting is trying to give some hints to your input and really convert your downstream task to what the model has already known. So it's kind of trying to condition the model and trying to get the already known knowledge from the model to do something reasonable during downstreaming stage. But it has some drawbacks, of course, because you can see here the prompting is kind of ad hoc, and we need to like human engineer something there. So you can use it that it was, or you can use it as like a question, or like what is the sentiment, and you have like a mask. So you have like various designs of the prompt, which is a little bit headache because you have to suffer from trials and errors. So that's why people tend to use like a newer technique called prompt tuning, which is kind of natural because it just like converts the discrete fixed prompts to continuous learnable prompts, or called soft prompt. So on the left is the like usual paradigm of like fine-tuning the whole pre-trained language model, and on the right is the idea of prompt tuning. So just like what we have in L2P, so in prompt tuning, the pre-trained language model. Oh, sorry, my dog is barking. So the pre-trained language model is kind of fixed, and we just add some learnable instructions for utilized knowledge in the pre-trained language model to your original input. So for every input, we just add the same, for example, here, 2 learnable parameters or 2 learnable tokens here, so that we just need to fine tune those 2 parameters. And they're very small and learnable and scalable to different downstreaming tasks. And that's been very successful actually in the transfer learning paradigm. And by only like fine tuning on those 2 small parameters, it can do very well, even comparable to the full model fine tuning here. So it's kind of very interesting, but not clear how to utilize it in continual learning. So that's why we come up with our L2P. So we have like a nice animation like that is created by one of my colleagues at Google, and you can see here it will like eternally like iterate through a task A, B, and C. So you can see here every time you got a task, you got an input from a task, it will first generate the query as you see here, like and then use the query to choose some of the prompting parameters from the shared prompt pool. So for example, each input will choose maybe different prompts based on the query it generates, and then it'll just prepend the chosen prompts to the its original representations generated by the pre-trained transformer embedding layer, and then all the things adds up together will be put to the pre-trained transformer encoder backbone, and finally go to the classifier for prediction. So actually, when doing this kind of dynamic key value paired matching, we only need to train the parameters in the shared prompt pool as well as the classifier, and that's it. It's kind of like a simple idea, and I'll go into more detail later. So here, it's kind of like a more detailed illustration of the whole process. So let me go it one by one. So when we have input, for example, you can imagine it as a image, because mainly we're doing it for computer vision tasks. We first kind of convert the input to a specific key, which is like a condensed representation of your input by some query function. So here, we would like the key to actually contain some representative information from the input. So in our paper, a natural choice is actually the pre-trained transformer. So there's no prompting, any kinds of prompting there. We just use the whole pre-trained transformer architecture as the query function. So actually the key for input is not learnable. It's just like a feature representation we got from the input. Okay, and for every gray dot in the prompt pool, it's actually a key valued pair, and all the key and the values here are actually learnable things. So what we do here after we get the input key is to we kind of find the top n most similar keys based on, for example, cosine similarity in the key space, because you know that every dot is a key value pair. So for now, we're not using the value, we're just using the key. And we kind of match, for example here, the top three keys. And then after we do the matching, we kind of, here we can throw the keys away. We can just use the value. So the values themselves are actually prompts. So we just prepend the selected prompts, as we just said, to the input embedding tokens. And then, so for every time a different input comes, it will be first converted to a different key and trying to map to different prompts to use. So how can we kind of make sure that whenever two inputs are similar, they tends to choose similar match keys? So during the training stage, we're trying to optimize the key as well, because we would like every time when an input comes that is similar to the input we have trained, we would like the key to match more or less the same set of keys, or at least similar sets of keys. So we in the training stage, we will have a cosine similarity loss, and we're trying to pull the match keys closer to the query key or the input key. So basically all the keys are randomly initialized at the very beginning, but during the optimization process, the keys will be pulled to their matched input keys. So they will be more and more concentrated during the optimization process. And finally, what we want to achieve is kind of here. If we have two inputs, input 1 and input 2. So here we don't have the idea of different tasks, so they may or may not from the same task. So input key is kind of mapped to a key called K1 and input 2 to K2. They are mapped to, you can see, two different sets of keys. But I just pick a random demonstration example here. So there might be something in common between the two set of match keys, which is the shared prompt. We can So we believe it encodes some of the generic features, at least between the input 1 and input 2. And also here's some unshared prompts between input 1 and input 2. And I believe it encodes some of the, actually I should call this input specific features, because we actually have no like clear definition of what the task is in our L2P learning process. And actually we can do the so-called task agnostic learning, meaning that we can just blur the task boundary and let them let the L2P algorithm to figure out the difference between the instances. Okay, so here's the overall learning objective of L2P. So as I just said, the first part is just like conventional classification laws, trying to optimize the prompts as well as the final classifier. And the second part of the loss is the pool loss that I just mentioned, to optimize the keys so that every time like an input key matches to like a set of chosen keys, those set of chosen keys will be pulled closer and closer to the matched input key. So, okay, yeah, let me go to some like experimental result that we got in L2P. So as I just said, L2P can be worked with no rehearsal buffer at all, or it can be simply combined with rehearsal because it's like a orthogonal technology. So here we can see from the first red row, without rehearsal buffer, we can do like very well compared against some like old regularization-based method, because they're like compatible with no rehearsal buffer. And we also try to compare our method against the rehearsal-based method. But of course, we add the same rehearsal buffer as well. And we can see here, when the rehearsal buffer is larger, the gap between our method and the rehearsal-based method are kind of smaller and smaller, which is kind of predictable, because in the limit sense, right, we have like used the upper bound, meaning that we just use the IID training on all tasks. If you have like an infinite size of rehearsal buffer, you can just put all the data at once, and that's why you can get the so-called upper bound performance. And finally, I believe all the rehearsal-based method will converge to this number, and if we have like a finite size of buffer. And we can see here, actually the like the difference between like our method and the upper bound method is very close, and which is like a good sign. Okay, and we also have like experiments on the domain incremental benchmark, which is on the core 50, a good like continual learning benchmark on the domain incremental task, meaning that the actually objects are actually from different domains. You can see here they have like different backgrounds, lightning conditions, so on and so forth. And in this task, L2P actually, of course, plus some like rehearsal buffer, got like very amazing performance. It's only like 1% less than the upper bound performance. And here's also another very interesting task actually. It's the so-called task agnostic setting. That is from like another archive paper. In that paper, they proposed like the so-called Gaussian C500 dataset. You can see here, you can just regard the x-axis as the timeline, and the curves here are actually probability density functions of each class during time. So you can see here at each time step, you have like different mixture, like components of different classes. So the actual distribution of the mixtures are changing like in a more continuous way than what we have in the like domain or class incremental setting. So this is actually a quite interesting and challenging benchmark. And again, our L2P can do very well on this setting. because as I said, we don't have the concept of actual task when we do the key value paired matching. We only want to, we actually do it at a like a instance level. Okay, so let's see some possible limitations of L2P. So L2P is like a pioneer work that brings prompts to the continual learning setting, but actually it tries to maintain a single prompt pool. Although we have the idea of like sharing prompts between different examples, there will be inevitable interference between the task-specific and task-invariant knowledge, because even if like two examples share something or unshare something, and when there will be more and more examples coming, the idea of shared and unshared prompts will be blurred, and eventually, actually, all the prompts will be shared between some of the pairs. So there will be like inevitable interference between the prompts. And also, the prompting design in L2P is quite preliminary, I would have to say, because we only attach prompt at the very first input layer, so that the representation power of the prompts are somewhat limited. And also, we choose to use the original prompt tuning style, which is directly prepends prompts to the input tokens. That might not be the best choice, because if you think about L2P, when adding prompts, we're actually adding the length of the feature representation. So if we want to expand it to a multi-layer setting, the length of the internal representation will grow like bigger and bigger again. So which is like a kind of key factor to prevent it from like scaling to multiple layers. And also L2P, from the performance perspective, it still needs a rehearsal buffer to actually outperform rehearsal-based method. Okay, so here's what some of the highlights of the DualPrompt work. So we actually have like a novel design based on the prompt pool of the complementary style of prompts. So we have general prompts and expert prompts. There are two kind of prompts to encode task-invariant and task-specific knowledge, respectively. And in our work, we have done like a comprehensive empirical study on the design choices of prompting, about where and how to actually attach prompts, not only in the very first input layer, but throughout all the pre-trained transformer-based backbone. And excitingly, DualPrompt can be state-of-the-art rehearsal-based method, even without any rehearsal buffer. And in this work, we also introduced like a new challenging continual learning benchmark based on something that's already there, called split ImageNet R, which is kind of more difficult actually than the original ImageNet R. ImageNet dataset, and it's like pretty good for ImageNet pre-trained models, because it's something different, and we can actually reliably evaluate our model on this split ImageNet R dataset. Okay, so what is the motivation of DualPrompt? So the motivation is actually coming from the complementary learning systems. And I believe there are like a bunch of work discussing complementary learning system, both in the like neuroscience literatures and continual learning literatures. So it's kind of like an old idea, actually. It kind of decouples the process of human learning into like two process through like two functionality organs. So it kind of decomposes the human learning into fast learning and slow learning. During the fast learning process, from my personal understanding, it kind of learns some task-specific knowledge, because in the human learning process, the tasks are changing very soon every day. When you like playing something on a computer, when you're reading books, you switch tasks very, very quickly during your everyday life. So you need to have this fast learning ability to pick up knowledge from different tasks. And also here's like task invariant knowledge, which is built very slowly in your brain. So when you see different tasks, you're actually learning something internally. So whenever like a coming new tasks you'll be facing, there's already something in your head that you can directly leverage, which is the so-called task-invariant knowledge that can be shared among different tasks. So that's why we would like to try to use the prompts to mimic the process of fast and slow learning. So we can start from the design of the prompts first. So the learnable parameters here, in green here, we have two prompts. The yellow one is the so-called G prompt. So we assume that we're doing it on like a class incremental setting. We have like a series of tasks, and all the tasks just share the same set of G prompt. So we can gradually build up the like general knowledge or general instructions in the G prompt. And here we have like a set of E prompt, and the actual T subscript here, big T here, is the number of tasks we have. So for each task, we have like a specific set of E or expert prompts for them, so that we can actually capture the task-specific knowledge from the certain task. And how can we determine an input from a specific task or not? We actually directly leverage the query mechanism that we use in L2P. So we just process the input from some query function, and we match it to like a specific learnable key, so that all the examples from the same task during training will be trained to match the specific key. And here we have these two kind of specific prompts, and we're actually doing like much more than what we have in L2P. Here we have multi-layered attaching, meaning that instead of have like a single prompt, no matter it's G prompt or E prompt, we actually can have like multiple prompts of them, and we can actually attach them to multiple different layers throughout the whole transformer. And what's more exciting is that because you have decoupled the two kinds of prompts, you can actually place it at different layers of the transformer. For example, the G prompts are better at capturing more generic features. And in our experimental setting, we kind of find that it would be better to put it to shallower layers, or layers that are more close to the input. And for the E prompt, it would be better to put it at like deeper layers to capture more like higher level of task-specific features. And also another thing that in DualPrompt is actually how to attach these kind of prompts. So recall that in L2P, we directly prepend the prompting parameters to the input embedding features. So from like the calculation perspective of attention, we actually, when calculating attention, self-attention, we just replicate the input to three pieces, to three exactly the same copies called query, key, and value, which is different, of course, different from the key-value pair we have seen in L2P. So it's kind of like internal attention term in there. So the previous way of attaching prompts is equivalent of like have three same copies of G prompts and prepend it to query, key, and value. But for now, the prefix tuning style is actually another popular paradigm in natural language processing, is to just split the parameters we already have here, and to prepend it to only the key and value. So if you actually do the self-attention calculation, you'll find that if you only add the prompting parameters to key and value, the actual output token length will remain the same, meaning that no matter how many layers you add, your final output token length will be the same as your input. So which is very friendly to our like multi-layered like expansion of the original prompting idea. So here's like a brief like comparison between DualPrompt and L2P. That's pretty much what I just said. So we can regard DualPrompt as a like more comprehensive study, come up after L2P, and to use it as more general framework to investigate how can we do better prompting in the continual learning scenario. Okay, so here's also what is something really important that I want to bring about is the split ImageNet R, a new challenging continual learning benchmark. So the idea of constructing the dataset is pretty much the same as what we have done in split CVPR or split ImageNet. So it has 10 tasks with 20 classes in each task, and you can see here the classes, the like intra-class diversity is very big. We have like different styles of lions here, for example, and they're actually very challenging and closer to real-world scenarios. And one thing I would like to bring about is that they are very unfriendly to those rehearsal-based methods. Because of the high intra-class diversity, you need to save actually a lot of the examples to actually work well. And it's even more challenging than what we have seen in the split CVPR dataset. And another thing is that it's very useful for actually evaluating the ImageNet pre-trained backbone, because our VIT actually is pre-trained on the ImageNet dataset, and split ImageNet R provides like an alternative way of like evaluating our model without like need to think about if there's any like data already there in the training set, right? So yeah, it could be served as a great alternative as the ImageNet dataset we have for continual learning. Yeah, and here's the experiment result I just mentioned, right? So here the curves are actually like a rehearsal-based method. If you look at the x-axis, it's the actual like size of the rehearsal buffer they use on like ImageNet, a split ImageNet R. So all this rehearsal-based method actually requires a very large buffer to perform well. But if you look at DualPrompt or even L2P, like without any memory buffer, it can still perform very well. And here, actually, if you notice that we're not like only referring to the buffer size, we actually convert all the additional memory size with the actual rehearsal buffer size used in different rehearsal-based methods. Okay. And here, this is actually kind of very interesting comparison between our prompting-based method and the architecture-based method. So previous architecture-based method, well, actually it's actually like a headache for me to find all the method and trying to compare them against our method, because as you can see here, the actual architecture and their experiment setting are more or less slightly different among these kind of methods. And it's very hard to have like a real apple-to-apple comparison. But I have tried our best to try to list all the different settings they use. Like they use different buffer size and they have like additional percentage of parameters, although we have different backbones. And here we can see that we can clearly see that actually the additional parameters of the prompting-based methods are actually very small, and the performance gain are huge over these existing architecture-based methods. Well, here is actually something I like the most for DualPrompt. It's actually the t-SNE visualization of the learned general and expert prompts. So on the top, here are like E prompts from different tasks. You can see that they're actually clustered very well, for different tasks. And on the bottom, it's actually the trajectory of G prompt during the training stage. Because know that we have like only have like a single G prompt that is shared among all tasks. So we cannot have like different clusters, but we can actually draw it after the training of each task. We can see here the G prompt itself the trajectory are actually moving very slowly during the training process, compared with the quite scattered, but of course centered around the task center, the ePrompts. So we can see like a direct visualization of the task-specific knowledge and the shareable or task-invariant knowledge here. Okay, so let's get to the conclusions and some future directions. So of course the conclusions here is like one sentence summarization of L2P and DualPrompt. L2P is the first ever work to introduce prompting to continual learning with a novel design of prompt pool and key value paired query mechanism. And DualPrompt improves the paradigm even better with complementary general and expert prompts and comprehensive study of where and how to attach prompts. And both methods actually do not require rehearsal buffer, although L2P and DualPrompt can, of course, perform better with the rehearsal buffer. And they have created state-of-the-art performance on multiple CL settings and benchmarks, and also the split image that are. We hope that it will further benefit the community to evaluate their continual learning model better in the future. And here's some possible actual future directions we can pursue after these two works, actually. So first of all, we can notice that both L2P and DualPrompt are transformer-based method. So how to generalize prompting-based continual learning, or even simple, even just prompting technique to more architectures remains to be a problem. Like how can we do it on multi-layer perceptron? How can we do it on ConvNets? We need to think more about how to transform this prompting technology. But I believe it's doable because we can think about prompting as like a conditioning variables to the full model backbone. We have like similar technologies in ConvNets as well. For example, the batch normalization could be like a small parameters that we can use to condition the backbone, for example. But we haven't like tried actually. And the natural extension is actually to apply the method to different domains, like natural language processing, because prompting is actually from it, and we're just trying to use it for vision tasks. We, of course, can apply it to natural language processing. And another interesting direction, actually I'm working on this, is the efficiency in continual learning, because both L2P and DualPrompts, we only care about the performance. We doesn't care about how fast you can do the training and the inference. And further, we can even compress the model a bit to make it even memory efficient on resource limited platforms. And we actually have a new paper called Sparse Continual Learning on the Edge, that talks about how can we do continual learning in a more efficient way. That is very interesting. And also we can actually explore more real world use cases for continual learning. And good news is that L2P has been used in some of the Google Cloud products already to address forgetting for those periodically updated models. And finally, we have some additional resources for you if you'd like to dig more about L2P and DualPrompt. We have the GitHub repo, as well as like a brief Google AI blog for L2P to illustrate our work. Okay, that's pretty much of it, and hopefully enjoy the talk. And it's the time for comments and questions.
Yeah.
Thank you so much.
That was outstanding. Thank you so much. And we have, I know, many questions. So I'll first start with Adi. I saw you had your hand raised at some point in the presentation. Would you like to unmute and ask your question or clarification?
Yes, thank you. Thank you for a very nice talk. I have a few questions for you.
Yeah.
The first one being, so in the dual prompt that you explained, there are separate, if I understand correctly, there are separate e-prompts, one for each task or maybe multiple for each task, while the g-prompts are fixed and shared across all the tasks. Is that right?
Yeah.
So how does this work in a task agnostic setting?
Well, yeah, you got the point. And we're actually only pushing forward like DualPrompt for the class incremental setting. Yeah. So that's the difference.
Even in that setting, how do you when you are given a new class or when you're given an unlabeled image, how do you find out which are my e-prompts for this unlabeled image?
Yeah, good question actually. So as I just mentioned, we actually use the query strategy that is from L2P. So first of all, we encode the input via some query function, which is the pre-trained transformer we have in our work, and we have some input key here. So we just match the input key to one of the like trainable keys for the EPROMs, so that we can do the match to choose which set of EPROMs to use.
Oh, I see. Because the number of classes you have seen till now is limited, and you have class specific EPROMs you can look up between them. I see.
Yeah, sure.
And one more follow-up, and this is about your more general experiments with the rehearsal-based approach. In those approaches, do you update the full network when you run, let's say, ER or GDUM?
Yeah, that's another good question, actually. Actually, in the experiments, we try to run both, actually, both the frozen backbone version and the totally free version. And we kind of find that they will perform a lot better when we just unfreeze the model backbone. So we just report the best number they have.
Got it.
Yeah,
thank you.
Sure. Yeah,
thanks again
thank
for
you
a nice presentation.
Yeah, thank you too for great questions.
Before we move to the other two members with their hands raised, just one quick clarification question from YouTube Live. Is VIT pre-trained on ImageNet 1K or ImageNet 21K?
Oh yeah, so actually we try to use it. So the numbers we got here is from ImageNet 21K. But when we if we only use like ImageNet 1K, we'll just like have slight accuracy drop, but not much.
Okay. Yeah. Great. Now the other two people with your raised hand, I guess technically Andre asked the first question if you want to unmute, but yeah, I'll let both of you have the opportunity to unmute and ask your question. So. Are you speaking, Andres? Oh, there we go. Okay, I can hear you now.
Yeah.
Great.
So thank you for the great presentation and the great work. I think that it is a great idea for this area, for this field. But yeah, I have one special question for you. It is regarding to the pre-trained. Yeah, you mentioned that you use an ImageNet pre-trained model to select the key, the prompts that you are going to use for every task, for every elements in the task.
Yeah.
I think that this is in this case, the ImageNet pre-trained or the model pre-trained on ImageNet, in this case, is not in both in Cypher and the other data, the other split that you tried. In this, the model is like an expert in this case. Is the model that in what you can prove is regarding to the decision to what prompt have been to use in this case.
Yeah.
So what happens if you, for example, try just with the bit pre-trained on ImageNet? What is the results? Or, for example, the zero-shot results of this model in both scenarios? If you, for example, have the task ID, for example, or just the zero-shot result. It is compared with what you have with the DualPrompt model or not?
Well, actually, not. The zero-shot result is actually a bit lower than what we have. So meaning that when predicting the actual keys, there will be like inevitable misclassifications, as you just said, right? If we treat it as like a classification model. Actually, we observed that it will be actually okay if you like kind of choose the wrong key somehow. Because our algorithm kind of has the tolerance of the mismatching between the input and the keys. So it's kind of all right. But I think you kind of bring like a very good question. Is the way that we use the query function is just to use the ImageNet pre-trained backbone, right? But actually, in real world, you have like multiple ways of choosing the query function, because you have your input, right? And you can choose like a lot of like different pre-trained feature representation models. So you can actually use like a ResNet here, or like different models if you really want to adapt it to like different use cases. You can always find like a pre-trained model which is more closer to your downstream task, so that you can actually find a better like key value paired matching in the case.
Yeah, I agree. I agree with that. But for example, imagine that you are working on in a domain that you don't have this big pre-training. For example, on video domain. For example, on video, it's very difficult to have a big training for the whole data set, or for the whole kind of data that you can see due to the big diversity of action in video. So in this case, how we can or how we can handle with this problem?
Yeah, well, I think we have kind of like underlying assumption of why this prompting technique will work, because if you look at the original like prompting technique, we're actually not like encoding very specific knowledge in the prompting parameters, because they are actually very small, right, compared to the main backbone. So underlying assumption is actually we have like already enough knowledge that is contained inside the model already. So we have to have like a relatively well pre-trained model, so that the prompting parameters can actually condition the model to gain the useful knowledge for the downstream task. As you just said, if the model itself is not pre-trained, we have to absorb knowledge like step by step. Of course, and we kind of tried the idea, and both L2P and DualPrompt will like suffer from the like insufficient of knowledge at the very beginning. Of course, we need to like unfreeze the backbone. Like gradually, when you train more and more, it will gradually build knowledge, and it can work better for the later tasks. So I think from like motivation perspective, I think you better have like a well pre-trained model to let the algorithm work for the downstream tasks.
Okay.
Yeah.
Thank you. Thank you very much.
Yeah, no problem. No problem.
Oh, great. And I guess, Prateek, do you want to unmute and ask your questions?
Hi. Hi. Thank you for the amazing talk. The explanations were like really clear. So my question is, I think half of my question was answered by the previous question that basically my question goes something like this, that so we have this query function, which is essentially trying to take the example and try to construct some sort of representation which could be matched with the prompt key, right? Mm-hmm. So now, and we are using a transformer, let's say any pre-trained model for that, right? So in this case, it's a VIT model, which is pre-trained. for the query function, or let's say some other ResNet model which is pre-trained on ImageNet. So now my question is that given that that model is a pre-trained model, that model will already have enough power to kind of generate features which can classify these split CVPR classes themselves based on those features. Like if you take those features and learn a KNN classifier over them or some sort of unsupervised clustering, it would classify most of the tasks correctly, is what I'm assuming, because it's a well pre-trained model. And CVPR is not that hard of a task. So then in that case, if you have a big enough pool of prompts such that each task can have basically, let's say you select top K for each example, and you have like 10 tasks. So you have like 10 times K or more than that prompts, then each task can potentially just select like individual prompts from this pool. And then basically, then in that case, it becomes something like this. The task identities are provided by a pre-trained model. You take an example, you try to classify it into like some classes, and then you can, and those IDs are given by that. And then basically you're using basically independent prompts. You're learning independent prompts for each of these tasks. So when you think of it that way, then my question is that one of the baselines where you kind of have like, let's say task identity is given to you and you like learn independent prompts for each task, that becomes a really crucial baseline. Like let's say I assume that the task identity is given to me and now I learn independent prompts for each of the tasks. Does this has any leverage or advantage? Like does L2P perform better than that case? And I also want to understand, like, do you think like that the query function is essentially providing the task ID implicitly? And if yes, then something like this could also be built into other continual learning methods, right?
Yeah, well, I think it's very great observation, actually. So what you just said is actually a very strong baseline, right? We call it like task, like maybe separate prompts, right? So given like you have the oracle, you have the ID, and we actually try to conduct some experiments on this case, and it turns out to be, let me check the performance. It turns out to be like a very strong baseline. Actually, if I remember correctly, for 600, it will achieve like somehow like 83 or something, and for the 5 data set, it'll achieve maybe even like 86 or something. Yeah. So in this way, we or maybe on 5 data sets will do even better, maybe 87. In a sense that you kind of train different prompts for different tasks, and you are kind of throw away the sharing knowledge ability between the prompts. So you just given the different tasks are somewhat independent, you can learn like you can train train the prompts separately on them. But actually, what we observe at least in the C500 case, because different tasks are actually similar to each other, right? And we find that actually like sharing prompts between the different tasks are more like beneficial. And we observe more improvement in the split C500 case than what we have in the 5 dataset case. So if you look at the 5 dataset, the difference between tasks are actually like much larger than what we have in split C500, meaning that there might be like less knowledge to share between tasks. And that's why we can do well, even if we have like separate like prompts for each task. Yeah, I'm not sure if that answered your question or not.
Yeah, it kind of partially addresses some of the things. So yeah, another question I had was that so now I'm thinking of it this way, that we have a query function which is a VIT model, and we have a classification model which is also a VIT model. So it's the same model. Yeah. So now let's say, I'm just like thinking out loud. So let's say now we are building upon the intuition that this model is able to generate good enough features which can be used to classify these tasks by themselves. Then I can also kind of think of it this way, that the other model which is used for classification, that also has like enough power to actually generate features which are representative to classify the task. So in that case, the zero-shot performance of the model becomes like even more important to evaluate on something like this, or maybe something like where you learn like, let's say you learn prompts for one task and then you just use those prompts for all the other tasks without training them at all. Like how does something like that work? Because if the sharing is, if the tasks are very similar and the query function is already like good enough, then just doing that, something like that might work without doing anything else. So now my question is that like, have you like tried on like some data sets which are like more challenging in that sense for pre-trained models, because CFAR 100 might not be a very challenging kind of a data set for a pre-trained model in some sense.
Yeah. So yeah, good question. So, and I think that is the reason why we have the split image at R. So I'm not sure if you noticed this data set we have. So apparently it's much more challenging than the CVPR 100, and it's even very challenging for the ImageNet pre-trained models. And here's the actual performance we got. Does that answer your question?
Yeah, thank you.
Okay, yeah, cool.
Okay. Are there any more questions? Great. Well, I guess we're a little bit over, so this will be a good time for us to go ahead and wrap things up. Thank you, everybody, for joining today, both on MS Teams and on YouTube Live. Thank you, Zifang, for this wonderful presentation. You can join us next week at the same time and the same place for our next Continual Learning Seminar presentation. So see you next week, everybody.
Yeah, thank you. Thank you, guys.
Thank you.